Entropy generation associated with a heat transfer. A frictionless piston cylinder device contains a saturated liquid vapor mixture of water at 100 degrees C. When I first read the first sentence, I notice frictionless and saturated mixture. Those things tells me that, first of all, frictionless signifies you eliminate irreversibilities, and its system is also going through a constant temperature and a constant pressure process, basically an isothermal process, because remember, the system is undergoing a phase transformation that happens at 100 degrees C. So basically there are no irreversibilities in your system. During a constant pressure process, a 600 kilojoule of heat is transferred to the surrounding air at 25. As a result, part of water vapor contained condenses. Determine the entropy change of water and the total entropy generation during this heat transfer. Well, let's start with the first one. The entropy change of water. The entropy changes because there is a heat transfer going out. So I expect, since the heat energy carries entropy with it, you expect the system's entropy to change. And also you need to remember the process is isothermal. The temperature is constant. And in previous lecture, we learned that in order for me to calculate the change in the entropy of a system, I can write it with this equation, Q over T, because remember in differential forms we said ds was equal to delta Q over T. For us to be able to get our temperature outside of the integral, this needs to be constant. And for isothermal processes then, we need to write it like this. So for isothermal processes, if you want to get this out, it gets out like that. S is equal to Q over T. Now, but for you to write this equal sign here, you need to know that the system is basically reversible. And in this case, everything given in the problem signifies this process is reversible. Now, in this equation, though, the Q should have to include the sign, because think about it, when the heat energy is getting out, you need to expect an entropy drop in your system. So you need to say minus. So entropy is lowered, minus 600 over the Kelvin scale temperature of the boundary, which should be 100 degrees C, because it's an isothermal process. So overall, when you calculate the entropy change in your system, it is a negative volume. Entropy decreased because the heat got out. Heat carried entropy with it. So the next thing asked in the problem is the total entropy generation. When we are talking about total entropy generation, you need to consider what we call an extended system. The system plus its immediate surroundings. So instead of taking the boundary here, now we include the immediate surroundings and taking the boundary like around this region, and analyzing the system again. That will help us to include the changes in the next to the immediate surroundings of the system. System plus the surroundings included. So what happens is then, basically, when I extend the system, I can write the entropy balance. Because it's asked the total entropy generation. Basically, it is asking the entropy generation term, but it's asking it for the total entropy generation. So it tells you that when you see the total, it means that include the immediate surroundings. Basically, work on an extended system. Okay, so when you write the entropy balance, including the overall on the extended system, then you can say the same thing, right? The entropy getting in, entropy getting out should be a plus equal to entropy generation, should be equal to the change in the entropy of the system. Now, okay, now since it is in like immediate surroundings, the entropy is not getting in because there is no heat getting in, but the entropy is getting out because heat is carried out. So it is basically, this term is basically minus Q out over TB, temperature of the boundary, and the Q out is here basically, it doesn't have a sign convention, it just gives you with the subscript, it's getting out, so you don't need to use a minus 600, 600 is enough. It is the correct case here. So plus the entropy generation should be equal to the change of the entropy of the system. Rewrite the equation. The entropy generation term goes to left hand side, and we can calculate this term because we know the Q is 600, but now the boundary temperature is changed, it becomes 25 degrees C, and it's because you are now in the surrounding temperature. Okay, so plus the change in the entropy of the system, which is we already calculated, and from that information, with including the extended system, you were able to calculate the entropy generation term. And notice that even the system is decreases its entropy because the heat is getting out. When you include the extended system, you see actually entropy is increasing. Okay. This tells you that even the system is internally reversible. When you actually look at the surrounding, you are increasing the entropy of the surrounding. So in total, entropy is always increasing.